Hello, this is your instructor Joe again, and I'm going to cover Chapter 7. Chapter 7 is on the network reference models and standards. So in this chapter we're going to be able to, after we complete all the assignments, we should be able to describe the ISO and IEEE 802 networking models and summarize the networking standards. We'll go ahead and get started. So we have this model that you need to know. It'll come up in all of your classes from now on. It's called the OSI reference model. It's got 7 layers. It was proposed by the International Organization for Standards, and it provides a common framework for the developers, and it also gives you a visual representation to work with and to learn from. The OSI model is not specific to any protocol suite, so it's not really implemented. It's just a framework. It's a model that you can use to develop your own networking protocols on. So the reason this came about was back in the 60s, we had all of these giant mainframe computers, and we had like 5 big computer companies that made these mainframe computers. Companies such as IBM and Digital, HP, I think made some mainframe computers. So we have all of these companies doing their own thing, making their mainframe computer. The problem is when you do your own thing, your products don't necessarily work with other people's products. So once a company had chosen one of these manufacturers to make their mainframe, the company was kind of locked into buying their equipment from then on. So for instance, if I bought an IBM mainframe, I wouldn't be able to go and buy a digital dumb terminal or printers that would work with the IBM system. So we had all these different systems that had different architectures. And ISO came up with this OSI reference model so that these manufacturers could come together, and if they followed the same model with their products, then their products would be able to speak with one another. They would be interoperable. So that means that I could buy equipment from other manufacturers, and it would work with other manufacturers' equipment. Think today of wireless devices. If you go and buy a Linksys wireless router, you don't have to buy Linksys wireless cards and all of the devices that you have. You can buy network cards or have network cards in your Wii or your PlayStation from all kinds of different manufacturers, and it still works. So this was the reason they brought about this reference model that we're going to cover today. So there's reference models and standards all over the place around you. You may not you may not realize it. The book gives an example of the United States Postal Service. So it says to see the value of a layered model outside the field of networking, look at the post office. The letter has to be written. Then you put the letter in an envelope and put addresses on the outside of it. You have to put a stamp on the envelope. The post office in the destination town has to sort the letter correctly based on the zip code to get it to the right destination. The post office in the post office in probably the origination town where you were sending it from has to sort it, and then the post office in the destination town has to sort the letter correctly for the right part of the town. The local carrier has to deliver the letter to the correct house. The recipient has to receive the letter, open it, and understand it. So you can see here we have a multi-step or multi-layered process to deliver a piece of mail from one house to another. And it's exactly the same with a packet that's going across the network. We need this layered approach so that we can take that packet, route it across the entire planet, and then deliver it to a computer on the other side of the planet. One of the things that you need to realize about the OSI reference model is that each task of the previous layer can be handled separately without affecting the procedures of other layers. For instance, one of the layers that we have is an application layer. And programmers typically work at the application layer when they write their software. But we also have a lower layer called the network layer. The network layer consists of routers. Now, if we look at this model, when you're writing your software, you need not be concerned about what type of router your application that you write is going to cross when you're trying to deliver your packet from one computer to another. That's because these functions are layered and separated so that I don't have to worry about all the lower layers if I'm working at one of the layers. So I can write my software. I don't have to care about what router switches, whether you're using wireless, whether you're using fiber optic, whether you're using copper cable. I don't care, because the model is layered so that I can just focus on my layer, my responsibility, and then other people can worry about the other layers. And here is our OSI reference model. You need to be able to remember these layers, and you need to be able to remember them in order. People come up with all kinds of sayings to be able to do that. What they typically do is take the first letter of each word and make an acrostic. Let's see. So some people say all people seem to need data processing. So that first letter will help you remember what the word is, and also help you to remember the order in which these layers go. So you have to memorize them. You can memorize them from top to bottom or bottom to top. If you memorize them from bottom to top, they say, please do not throw sausage pizza away. That's another saying that you can use to remember it. You just need to be able to remember it, which one's on the bottom, which one's on the top, the names of the layers, and the order in which they come. And you will have this in every class that you have from now on. So you might as well just go ahead and do it now. All right. So in order to troubleshoot networking, in order to comprehend how networks work as a whole, you need to know what each layer does, what components, networking components, routers, switches, hubs, and devices operate at each layer. So if I'm having a problem with a printer, it's going to be at a certain layer that I can troubleshoot. You need to know how the layers interact with one another. Each layer in an OSI model has its own set of functions. That means it does certain jobs. So the application layer has its own job. The presentation layer has its own job. In the previous chapters, we talked about the TCP/IP model. The TCP/IP model is based on the OSI model. So, if you notice, the OSI model had 7 layers. The TCP/IP model has only 4 layers. So the functions of the application, presentation, and session layers of the OSI model are all wrapped into one application layer in the TCP/IP model. The transport layer matches the transport layer 1 for 1. The network layer matches 1 for 1. And then the data link and physical layer are all wrapped into the network access layer. So this IP model was born out of the OSI model. So this one was put into place first, and then they built this based on the OSI model. So they didn't use 7 layers, they only used 4 layers. But what they did is they included the functionality of these 4 layers of the OSI model into 1 layer. Or 3 layers. I'm sorry. The functionality of these 3 layers into 1 layer in the application layer of the TCP/IP model. These blocks right here are different protocols that we'll see. So for example, HTTP that we use to browse websites lives at the application layer. And you'll notice that that's where the web pages are programmed. So programmers generally deal with just this layer by itself. So the programmers generally deal with this layer by itself, and the networkers are responsible for all of these layers below. If we look in one of the dialog boxes, this is one of the examples. The setting in this configure dialog box here sets the configuration parameters of the physical and data link layers. The client for Microsoft Networks works at the session, presentation, and application layers. And these two, IP version 4, IP version 6, work at the network and transport layers. So we can see when we open up the network dialog box and configure the network dialog box, we're changing all of the settings for all of the 7 layers in one place. So logically, what happens is when you have a message, so let's make a packet. So we have a message that we want to send from computer A to computer B. It's going to travel down this OSI model to all these different layers, okay, where it's going to be sent across the network. It's going to get to the other side of the network, all the wires, and then come back up the network stack. And then what's going to happen is it's going to unwrap it and get the original message back. So your packet has to go through all of these layers, be put out onto the wire, and then come back through all of these other layers. Right? During the communication, these layers talk to one another in the different computers. So my network layer talks to the network layer of the other computer that I'm communicating with. Okay. Network layer is not going to talk with the application layer on another computer. They're going to talk directly with the layers on the peer's computer. Right. Remember, your data is divided into packets or data units suitable for each layer. Generally, these units that are broken up are called protocol data units. The protocol data unit is passed from one layer to another. At each layer, I add more information to the protocol data unit. Right? It's called a header. So, for instance, when we get to the network layer, we're going to stamp the source and destination IP address onto the protocol data unit. It's going to put that in a field called a header of the data. That process is called encapsulation. So encapsulation is putting things around your data. When the data arrives at the other computer, we have decapsulation. The computer that you're sending the protocol data unit to is going to strip off each layer. Just like when you open up the letter that you get from the post office. You take the envelope, you open it up, you throw away the envelope, and then you read the message. Okay, that's decapsulation. So at the top we have the application layer. This is layer 7. It provides the interfaces for applications to access the network. So it makes your application aware that there is a network that it can use. Okay? So the application layer is not like applications like Microsoft Word. Those actually live above the application layer. The application layer gives the interface or the method to be able to talk on the network. Okay? Generally, components at the application layer, one of the computers has a client component and the other computer has a server component. We've seen that with client-server networks. Some of the protocols you see at layer 7 are HTTP, which is for transferring web pages, FTP, which is for transferring general files, SMB, CIFS, which is network sharing, TFTP, which is transferring files without authentication, and SMTP, which is what we use to transport email across the internet. The presentation layer, the layer directly under the application layer, handles the formatting and translation. So it converts the data into file formats. So you have the JPEG format, or the portable network graphics format, the PNG format, or the GIF or GIF format. All of those specifications for those types of files live at layer 6. Okay. We also do encryption at layer 6. So we're going to format it into a format that Microsoft Word can open, or your browser can open, but we're also going to perform encryption. We're going to scramble it so nobody can eavesdrop on our conversation. So the presentation layer is important. The session layer, layer 5, permits two computers to hold on ongoing communication called a session, so the applications on either end of the session can exchange data for as long as the session lasts. So it's kind of like the part that makes sure that the other computer is still there on the other end. This layer handles communication setup ahead of data transfer, so it's going to open up that connection, kind of like dialing the phone. And then it's going to do the teardown when the session ends. Right, so it's going to close the connection. Common functions at this layer are name lookup and user log on and log off. So when I log on to the system, it's going to set up a session for my user. It's going to check my username and password and open up that session and keep it open for me. All right. Transport layer. This is probably one of the more important layers. It makes sure that everything is going correctly. Right. So the transport layer manages data transfer from one application to another. It's the part that breaks your long message into small packets, okay, called segments. So it's going to take your application layer data and break it into segments. Transport layer includes flow control and acknowledgments to ensure reliability. So not only does it make sure that the packets or the segments get to the other end, it also makes sure that we're not overwhelming the other computer with too much information. Maybe it's a slow computer or a slow internet connection. We don't want to overwhelm them with data. So flow control makes sure that the other data can keep up with what I'm sending. Acknowledgments means that I'm going to get a packet back for every packet I send. If I don't get a response back saying the packet was received, then I'm going to send my message again. That is the job of the transport layer. The layer also handles resequencing segments. So it puts when you break a file up into parts and send it across the internet, most of the time it doesn't arrive at the other end in the right order. It may get the file in with the last part of the file first, and then the first part of the file last, and it's all jumbled together. It's going to handle putting that message back together in the right order. Okay. So here's an example. We break our data into smaller chunks. Here's our PDU, our data. And then I add on the header that has port information and sequencing information. I add this header to my data so that I can put it back together in the right order. And remember, that's called encapsulation when I add this header. So I have my data. When I add a header on from the transport layer, it becomes a segment. We call it something different. So some of the key fields in the header are the source and destination port numbers. The port numbers are important because it's the way I keep conversations between two computers separated. So I can have multiple things going on. I can have a web server and an email server running on the same box, and I can keep my communication between those two different programs separate by using port numbers. We have sequence and acknowledgement numbers that make sure that the every piece gets there and I have an acknowledgement for it. and it also lets me put the segments back in the correct order. That's what the sequence numbers do. The window size is a number that I can use to check to make sure I'm not overwhelming the other computer with too much information. The network layer, the layer that we've probably been talking about the most, is layer 3. It handles all of the addressing. Okay. And it translates the IP addresses into physical addresses or MAC addresses. It also performs a best path selection, so those are the routers, when it crosses the network. Software components working at this layer include ARP, IP, and ICMP. Okay. It says access control is handled at this layer also. When it's talking about access control, this is where we do firewall stuff. Right. Remember, your routers operate at this level. Okay. Sometimes I have a switch that has more, I guess you would say, personality or brains. And a switch can be a layer 3 switch that does some routing functions. Okay. So the switch in your house, the wireless router, is a switch and a router at the same time. So it's a layer 3 switch. It can see IP addresses. So here's our picture again, our data. We add a transport layer header. It becomes a segment. Then I add the network layer header. It becomes something called a packet. So it's not called a segment anymore. Once I put the header on from the network layer, it's called a packet. So we need to get that terminology correct. The data link layer, layer 2, we're almost to the bottom, works with frames and is intermediary between the network and physical layer. The MAC address lives at that layer. Remember, that's the burned in address on the network card. It's put there by the manufacturer. We also have something called a frame check sequence. Make sure that the PDU hasn't been mangled while it's in transit. So if the PDU has been destroyed or is corrupted, the frame check sequence lets me know that, and I can throw away that frame, that protocol data unit when it gets to the other side. I won't read it because I know it's messed up, because I have this check number to make sure that the PDU is intact. So here we go. We've got the data. Right? We already talked about that. That's at the application layer. Then the transport layer header gets put on. It's called a what? It's called a segment, right? It's not on this slide. So it's a segment. Then it becomes a packet when I put the network header on there. After I put the data link layer on there, it becomes a frame. Notice it also puts information at the end. So the frame check sequence is at the end of the packet, not the beginning. I'm sorry, the frame, not the packet. The data link contains the source and destination address, the physical one. So that source and destination MAC address. It also has that cyclic redundancy check that allows me to make sure that the data hasn't been altered or corrupted. The software component operating this layer is the driver. So when you install a NIC driver on the computer, it's operating at the data link layer. NICs and switches operate at this layer. Remember, at the network layer, we have routers. At the data link layer, we have switches and network cards. Last layer, or the bottom layer, is called a physical layer. It converts bits into singles, to electrical singles for outgoing messages, and electrical singles into bits for incoming messages. So this is the actual physical, real world wire layer. Okay. Wire media uses electrical pulses if we're using copper. Fiber optic uses light pulses. Wireless uses radio waves. Okay. So this layer specifies what type of cabling we're going to use, the frequency of the light pulses, the frequency of the radio waves, everything like that is at the physical layer. When I take the 0 and 1s and put them on a wave form, so we have 0s and 1s inside the computer. When we get on a wire, we have 0 volts and 5 volts. We make a square wave on baseband. So when we're working with copper wire, it looks like that. When I send it over a wireless network, it's going to look like that. That encoding from all of these 0s and 1s to a waveform happens at the physical layer. So here's a table that summarizes everything. I believe it's in your book too. Use this table to go over your different layers, what we call the data at different layers, the protocols that are used at those layers, what devices are used at those layers, and what the layers do. So this summarizes everything we just went over in these few slides. So we got packet, frame. When it goes on a physical network, we didn't talk about this, we said bits. Right? So segments, packets, frames, and bits. Then we have routers at the network layer, switches and NICs at the data link layer, and then we have hubs and repeaters at the physical layer. IEEE also makes networking standards. IEEE is an international organization. The Project 802, which defines all our networking, was introduced in 1980. So 802 is the year and the month of its inception when they first started working on it. That's why it's called Project 802. 802 predates the OSI model. So they've been putting it together before the OSI model. So this is the actual standards. So we're going to have the number IEEE 802, and then we're going to have a dot and then a sub standard. So 802.3 is Ethernet. So anytime I'm working with Ethernet cabling, 802.3 is what I'm going to look at. And then I have a sub chapter of that standard, which 802.3U is 100 base T Ethernet. So it's 100 megabits per second, twisted pair Ethernet. So 100 base T is what we typically use, what we call fast Ethernet. The ones you're most typically going to see is 802.3, which has to do with Ethernet, your wiring, and 802.11, which has to do with wireless. So these are the ones that you'll most likely see and need to know. 802.3. We don't use token ring anymore. We do, but not very often. 802.8, fiber optic technical advisory group. 802.11, we'll see. 802.15, that has to do with Bluetooth, I believe. WiMAX, we'll talk about that. 802.16. So each one of these standards has to do with the frequencies we can use, the encoding methods we can use when we transmit over wired and wireless networks. And if we follow those standards, like I said, our stuff will work with other manufacturers' stuff. The two lowest layers of the OSI model, that's going to be the physical and data link layers, define how computers attach to specific media. Right? The IEEE 802 specification expanded the data link layer into two more layers. One's called the logical link layer. One is called the MAC sublayer. So data link, when 802 came along, it broke up the data link layer into two more layers. LLC controls the communication between the logical interface and the upper OSI model layer. So it talks with the higher layers. And the MAC control layer manages access to the medium and uses those physical addresses, the MAC addresses, on the network card. Right. Here's a picture of what we just said. And that's it. So this chapter was a overview of standards that we use in networking. They're not very difficult to understand. The difficult part's going to be remembering the OSI model, the order in which it is stacked, the devices that work at each layer, and what the layers do. Okay. So that's the end of the lecture. I hope you got a lot out of it, and I hope to see you next week when we do another lecture.